let's go to the next theorem that is also important. So theorem 2. Energy eigenstates psi of x can be chosen to be real. So here it is. We mentioned that this differential equation allows for real solutions. There's no contradiction because there's no I in there. But now we say more, that even if you find a complex solution, you can work with real solutions. So what is the strategy here? Again, strategy. To have, so you get a complex solution, psi of x, and then you go about to prove that actually this complex solution implies the existence of two real solutions. So complex solution implies existence of two real solutions. So, and moreover, two real, I should say it better here, degenerate solutions. How could you prove that? Well, it probably would occur to you that you would take a solution and say, oh, this solves it, and then you would show that psi star also solves this equation, and then by linearity of the Schrödinger equation, you can form what we would call the real solution, formed by taking psi plus psi star and adding them, or the real solution that comes from the imaginary part. You see, the real and imaginary parts of a complex number are real. So is the case here as well, that I can take psi and psi star that are different, and the sum is real by construction. You put a star, and recalling that star of star gives nothing, you see that this function is equal to its star, so it's real. So is this one. This function, which is the imaginary part of the solution that you had, is also real. So you get two real solutions. Moreover, you can show that psi and psi star have the same energy. Therefore, psi r and psi im have the same energy. So I'm really skipping very little, but I don't want to clutter the blackboard with the whole derivation at this moment. So here is the strategy. A complex solution implies two real solutions. And therefore, since you have real solutions, you can always choose them to be real. No loss of generality. You had a complex solution. You say, I like just real solutions, and you choose your two real solutions. You give them. You've given the whole thing. But then there is a nice corollary for the case of one-dimension bound states. So this is the part that is perhaps somewhat interesting. And the corollary is that if you're talking bound states of one dimensions, any solution is equal to a real solution up to a constant. That means, well, what's the difference? Let's write it down and look at it. Corollary for bound states of one-dimensional potentials, dim potentials, any solution is up to a constant phase equal to a real solution. So how does that go? Maybe you can use more of this blackboard. Why would any solution be up to a phase equal to a real solution? Okay, if you have suppose you have these two solutions here. Well, this is real, so that's trivially true, and this is real. But what if I put a linear combination of them, or take the original complex solution? Why would it be up to a phase equal to a real solution? The answer is the following. Because of theorem 1, that there's no degeneracy, you've got two solutions that claim to be different and degenerate, but that can't be. So by theorem 1, you must have that, in the notation that I have here, psi imaginary of x must be equal to a constant times time real of x. Now, if these functions anyway are real, the constant here must be real. Therefore, even if you form the original complex solution, psi, which is psi real plus I psi imaginary, you can check that. It's clear by definition that that's the way it should be. If you take this, this is equal to 1 plus I times c times psi real of x. Therefore, this is equal to a constant times the phase of, this is a complex number, so this is yet another constant that we could say the norm of 1 plus IC times some phase times psi r of x. So you see that any solution, any linear combination, in fact, with any numbers of psi r and psi imaginary will be a constant times a phase times this thing. So it is really just real anyway. So you can just you have just one solution, and any solution that you may write that represents a bound state is up to a phase equal to a real solution. Okay, so that's our theorem 2. Theorem 3. It's also very famous. If the potential v of x is even, that is v of minus x is equal to v of x, the eigenstates can be chosen to be even or odd under x to minus x. Okay, so here is another claim. So the potential is even. There's no theorems for odd potentials, no clear theorems, no simple theorems for odd potentials. But if the potential is even, the claim is that you can choose eigenstates to be even or odd. You know, the word chosen is very important here. Otherwise, this would not be a precise statement. You cannot say the eigenstates are even or odd. You can choose them to be. So how does the proof go? Strategy. Begin with a wave function, psi of x, that is neither even nor odd. Even nor odd. And then you do a little work with the Schrodinger equation. Take the Schrodinger equation, change all x's to minus x's, and show that, in fact, not only psi of x is a solution, but psi of minus x is also a solution with the same energy. So prove that psi of minus x is a solution with the same energy. And in this case, of course, we can already have shown that we can choose these wave functions to be real. So we can choose all of these wave functions to be real. And what do we do next? If we have these two solutions with the same energy, then you can build a psi s, which is 1/2 of psi of x plus psi of minus x, and a psi a for S for symmetric and A for antisymmetric, and a psi A that is 1/2 of psi of x minus psi of minus x. And these two would be this even under the exchange of x for minus x, this one odd under the exchange of x for minus x. And both would be solutions by superposition, and both would have the same energy. So that's the end of the theorem, because then these things are even or odd and have the same energy. So you can, the solutions can be chosen to be even or odd under x. So if you've proven this, you got it already. But now we get a corollary. For bound states in one dimension, the solutions, not anymore the word chosen, we can delete the word chosen. The solutions are either odd or even. So it's a lot stronger. It's not anymore you can choose them to be, but a general one is neither odd nor even. No, you try to find a solution that is neither odd nor even, and you can't find it. So it's very strong. Yes?
This is for
even potentials, yes. For bound state in one dimension with even potentials. V of x, V of minus x equal V of x, yes. So how do we show that? Well, again, you got two solutions here that are degenerate, that have the same energy, psi of x and psi of minus x. So given that there's no degeneracy in one-dimensional problems, this thing that they have the same energy, the only thing that can be happening is that psi of minus x is equal to a constant times psi of x, where this constant is real. Why real? Because we said already by the previous theorem, wave functions can be chosen to be real. So you've got this thing already, that this is true. Psi of minus x is equal to c times psi of x. Which, if you use this property again by saying, oh, but psi of x is equal to c times psi of minus x. Basically, what this says is that you can change the sign of the argument by putting an extra c. So you do it again. Psi of x is equal to this. So this is c squared times psi of minus x. So c squared must be equal to 1. And therefore, c is equal to either plus or minus 1. No other option. So the functions are either even or odd, but they can't be arbitrary. This point is sufficiently subtle that part 2 general exam at MIT 10 years ago had a question like that, and the person that invented the problem claimed that there would be a solution that could be neither even nor odd. So even faculty members at MIT sometimes get this wrong. It's not as weak as this that can be chosen, but it's really either or other in the case you have one dimension.